So back to Ethernet. So 64 byte time, remember that 64 byte is equal to 512 bits, which is equal to 51.2 microsecond. And somebody can do the calculation, please. Everybody do the calculation. How long is the 512 bits for 10 megabits? Okay, 1 megabit is 10 raised to 6, 10 megabit is 10 raised to 7. So 10 raised to 7 bits per second, 512 bits is how much? I know. Let me see if I can change it. Now basically, can you see it now, or is gone forever? You're back? Okay. Alright, because it says on my screen, it said that the connection is unstable, and then it came back. So I cannot see the Wi-Fi signal on my computer while using the using the PowerPoint. So you will have to just remind me if you totally lose the connection. I don't know, if you totally lose the connection, I will probably not hear the chat, or I will not hear the audio as well. So you will have to you have to call me or something. But anyways, let's proceed. So 512 bits, how long would that be? Anybody? 512 bits at 10 megabits per second. Okay, so I will do the calculation for you. 10 megabits is 0.1 microsecond per bit. Okay, 0.1 microsecond per bit. 512 bits would be 51 microseconds, 51.2 microseconds, just straightforward. Anyway, that is it will be required in the next slide. Second thing is they decided that they will do truncated binary backoff. And truncated binary backoff basically means that we will go by a factor of 2 every time we back off more than before, except after 10 we will not go more, and that after 16 we will not do anything at all. Okay, so you can try up to 16 times, but you take the minimum of the back off number and 10, and then you 2 raised to that minus 1. Basically the minus 1 is actually at the bottom, not on the exponent. So that is truncated binary backoff. And then the collision is detected. Whenever there is a collision, you detect it because you are not getting what you sent. Voltage is higher than what you sent. And then you send a jam signal. And the jam signal has to be, I'm sorry, go ahead. You lost it for 10 seconds. Let me just, I'm going to, I don't know, if I disconnect and connect again to another Wi-Fi, then probably it will be more trouble. So today we are going to have trouble this one. What can we do? Not much. We'll have to just stay with that. This is a big hotel, Hilton, and the Wi-Fi is called AT&T Wi-Fi. So should be a good Wi-Fi, I suppose. The signal when I measured it was 33 dB, which is supposed to be good, but probably their system is not very stable. And the reason is that there are 2,000 people or maybe 1,000 people in this hotel today for this conference, and so they're all they're overloaded. All right, let's just do the best we can, and next time I will think of something better than this. All right, so where are we now? We are back to slide number 20. So this one explains the previous slide in much more detail. Okay, so this is a flow chart. We start with counter equal to 0, means this counter counts how many times we have retried. So we haven't retried anything. When we want to send a packet, the counter is 0. We go and check, is the medium idle? Okay, is the medium idle? And if the medium is idle, then we proceed downwards where we start the transmission. If the medium is busy, then we just wait and then come back and check again whether the medium is idle. Now it says that we wait one slot, and whenever we say slot, that means 51.2 microsecond. Okay, the time is not slotted, the time is continuous, but when we start waiting, we just wait for one slot, 51.2 microsecond from whatever time we were in. And then we check the medium idle. If the medium is not idle, we wait one more slot, and we made one more slot, we wait one more slot. We keep doing that until the medium is idle. At that point, as soon as now the thing is not as soon as, basically what will happen is everybody's slot is at different time. Okay, so yeah, it just tells me once, and then hopefully we will just 15 seconds we'll repeat it. So basically everybody's clock is different, and so somebody will sense the medium is idle and they will start the transmission. If they are lucky, they will start the transmission, and then by the time your one slot is over, you will come and see the medium is still busy, and then you will wait again and again. Okay, but only by chance it is possible that when you start the transmission, the collision happens. Somebody else starts the transmission at the same time. You know why they could start? Because they are at the other end of the wire. So let's say the wire is just for the example, let's say it is 2 kilometers long. So the medium is idle at your end. Okay, what it means is that nobody near you is talking at all, but the guy at 2 kilometers also sees the medium idle, and they start talking, but you will not notice the collision until their signal comes to you. So this is important to know. The collision is detected only when somebody else's signal comes to you, and that takes time. How long does it take for the light or for the electricity to travel 2 kilometers? Actually, let me start with 2.5 kilometers. So if somebody is 2.5 kilometers and they said something, and the electricity travels, and everybody should remember the rate, because even though the first exam is over, the propagation delay is for lifetime. You have to remember the rate. For electricity, the rate is, what is the rate? Anybody remembers? If they can say it loudly. Nobody remembers that what is the speed of light and what is the speed of electricity in copper? Okay. Does the person have a microphone, or I mean I had a hard time hearing. Okay, so okay, here is the thing now. Yes, you can have one microphone, and one microphone can be with the class. The one which is good one can be with the class. The one which has a loose end, you can keep yourself, and then you can repeat if necessary. All right. So what was the answer that was given? Jas? Okay, that is not audible at all. Previous one was better. All right, so I am just going to tell you the answer. The answer is 200 meters per microsecond. 250. 250 is the electricity in copper, 200 is the light in fiber, and 300 is the light in air. Okay, those three numbers we remember. So 250 meters per second. So 2.5 kilometers, you can divide 2.5 kilometer and how long it will take. Okay, and then you have to have some safety factor. So anyway, they calculated that we should wait 51 microsecond. Okay, with safety factors. So basically it might take 51 microsecond if you limit the length to 2.5 kilometer. If you make the length, let's say 5 kilometer, then they are far away, and then it will take more time for their signal to come to you. Okay, if you put them, like 200 kilometers, it will take even longer. So Ethernet people said that we will limit it to 2.5 kilometer, and 2.5 kilometer divided by 250 is actually turns out to be 10 microsecond. But they said 51.2 microsecond is what we want the slot time to be. Okay, 5 times that. So, but that is related to the length. Okay, all right. Now going further. So collision during the transmission. So if you hear the collision during the transmission, then you send a jam signal, and the jam is also one slot. Why one slot? Jam is one slot because you want to make sure that the jam reaches the other end of the wire before you stop. Okay, because you are going to stop and the other guy should stop as well. So basically we use that 51.2 microsecond for jam as well as for waiting as well as for collision detection. Alright, once we send a jam, then we increment the counter by 1, right? And if it is more than 16, then we are done, we abort. If it is less than 16, then we use that to back off, and then the back off is calculated using that binary formula that we had in the previous slide, and you see if the medium is idle. Okay, so you back off using the binary formula on the previous slide, and then you check the medium again. Okay. Is there any question on this slide? Can you follow the flow chart? This is not a state diagram, this is simply a flow chart. Okay, so the K was the counter. So in the next slide, we use the word counter, and that is K here. The counter is the K. Now what is K, or what is the counter? Counter is the number of attempts you have made for this frame. We start with K equal to 0, which means we haven't made any attempts yet. Okay, we are starting, and that time we are not backing off. If there is a collision, then the K becomes 1. Okay, the counter goes up by 1. Now the next time when we start, we have to draw a random number between 0 and 1. Why 1? Because 2 raised to minimum of K and 10 is just 2, and then minus 1 is 1. So 0 through 1. So we draw now these are all integer numbers, so we are not drawing 1.5 or anything. So between 0 and 1, when you draw a number, it will be either 0, 50% probability, or 1, 50% probability. Right? So we draw a random number between 0 and 1, and then we wait that many slots. So what this slide does, 21, it shows the actual propagation of signal. So first line shows that A starts transmitting, and the signal starts going in both directions, left and right. Okay. As the time progresses, the signal reaches B, but it doesn't reach C. Okay. C thinks that the medium is idle and it starts transmitting. Its signal starts propagating both sides, left and right. At some point, A's signal reaches C, and the C detects the collision. A has not detected the collision. Only C has detected the collision now, right? At this point, basically C's signal at the last slide, C's signal reaches A. Now that A detects the collision. Anyway, whoever detects the collision, they send this jam signal, which is clearly heard by everybody. So you can see how the signals propagate. Okay, that the signal doesn't reach the other side just instantly, it takes time. And we are talking about here microseconds. And so they said that the one-way delay would be 25.6 microsecond, and therefore twice that much is 51, and 25.6 microsecond is 2.5. No, it's not 2.5 kilometer. 2.5 kilometer divided by 250 would be more like 10 microsecond. So basically, there is a lot of safety factor built in here. Cable access network. So now we are off the Ethernet. I think we are off the Ethernet probably a bit too quickly in this book. But anyway, now the book goes on to cable access network, so we'll talk about that. cable, the way cable access works, and all of us actually right now in St. Louis have cable access because the other thing is very slow, DSL is slow. So cable access, the way it works is that they have a system in some place which we call cable head end on the left, cable head end, and that is called CMTS, cable modem termination system, CMTS. It's a big box, and from there a cable goes to every home, and on the right we see 4 homes. So on the left there is a downstream channel, and the bits are clearly marked which home they are going to. On the upstream, basically instead of using collision, in the upstream the slots are assigned, the bits are assigned basically. So if you want to, the thing on the right are the four homes, on the left is the cable company's head office, and there actually it may not be head office, it is some kind of hut somewhere, but so they have a CMTS system, and instead of using collisions and random access, they assign the slots, okay, both upstream and the downstream. So when some signal wants to come to, they want to send it to your home, they tell you beforehand, they tell you that okay, slot number 15, 13, 23 are yours. And then similarly they say that while on the upstream slot number 15 and 20 are yours. So they don't have the same slot, different slots for upstream and downstreams, and you just transmit in those slots. In the beginning all the slots used to be clear, and that means not encrypted, and that obviously did not go very far because people started seeing everybody else's traffic. So now it is all encrypted. So every home has a secret key that only that home's modem has, and therefore your modem can decrypt the traffic which is assigned to it. So basically whenever you have such a system where the central system assigns it, so then there is a big what we generally call a frame, and at the beginning of the frame everybody listens. So that is called map. Okay, media assignment something, okay, map. So in that map, in the beginning it will say that okay, house number 1 you have no slots, house number 2 you have slot number 5, house number 4 you have this slot, and so on and so forth. So all the assignments up and down are in the map. Okay, alright. So now it says data over the cable service frequency division, multiple channels over upstream and downstream. So now one point we didn't say was frequency division. Now the frequency division is there, but there is also time division. So every home, I mean there could be only so many homes on one frequency, and so there could be many frequencies both upstream and downstreams, and each frequency will have time slots like we talked about. So time division, multiple access in each upstream and downstream. Now some slots are assigned, some have contention. Now so what happens is for the upstream, now the upstream, by the way, I don't know whether we have used the word upstream before or not, but any times we say upstream, we are assuming that we are talking to something very high up like a cellular tower, and that means that whenever the mobile talks to the tower, it is upstream. Okay. Similarly here, when the home talks to the cable company, it is upstream, because I don't know, I mean cable company is probably at the same level as home, but they are high up. We assume they are high up, right, like that. So downstream map is assigned, and the request form is transmitted using random access. So basically what you do is, if you want to send a big file, a big data, whatever, you say, well, I need lots of slots, or I need 100 slots. The modem says I need 100 slots. Actually modem doesn't really know that it needs 100 slots, because the router knows much better what is going on. But anyway, when the modem's queue is full, it looks at its own queue and the queue is full, then it says, oh, I need, so many buffers, so many slots. So that is randomly set, okay? That is based, so there is a small period in the map where anybody can say anything, and so somebody can say, hey, I need 10 slots. Just like you raise hand right now, as at some point, so you can say, I need 10 slots during that time. And you might succeed and you may not succeed, okay? If you succeed, then you will get 10 slots. If you don't get, next time you ask again 10 slots. So anyway, sometime you will succeed and you will get the 10 slots assigned to you, and then you can use those to transmit information as well as for ask for more slots. So suppose you got 10 slots, you can use 9 slots for the information, and then you can ask for 10 more slots in the last one. Alright, so that's the communication that goes on between the CMTS and the home system. Okay, now, alright, any questions about this thing, cable access? None. In that case, I will just finish this module. And what we have done is we have finished section 6.3 of the book. And these are the 6 things we learned. First we learned is that when you have multiple users, we can use both TDMA. It says RFDMA. I would say TDMA and RFDMA. Generally, whenever you write and R, it could be written as R as well. But basically, we saw cable modem uses TDMA and FDMA both. Random access is better for data traffic. Now that is another thing, is that we don't want to assign something forever like they did in the phone network. The phone network, when they designed first time, every slot is assigned to a particular user whether they use it or not. So there are 24 slots, let's say, for 24 homes, and yours is slot number 1. Even if you're not talking, the slot number 1 is yours. Okay, that was the beginning, right? And then later on they felt that this is not good for data traffic. It is actually not very good for voice traffic either, because you may not be talking even though your connection is on. But anyway, right now everything is data. Even the voice has become data. So Aloha has an efficiency of 1/2e. So you remember that protocol at Hawaii, which was called Aloha protocol, and that has efficiency of 1/2e, which is 18%. If you make it slotted, and in that case slotted means that you just talk only at the beginning of the slot, and that makes the efficiency go up by a factor of 2 to 1/e, 36%. Then we said that Ethernet does not really use slotted Aloha. It uses carrier sense multiple access with collision detection, and that has much higher efficiency. In the worst case, people were saying in those days in 1980s that, oh, only 38% is what you will get. But I think we get much better because there are not that many collisions actually. And now I wish this book would have discussed more about Ethernet, which we do in the advanced class, where we show that we don't use CSMA CD anymore, but what we use is, we'll take another chapter, so I'm not going to go there. But anyway, 802.3 uses CSMA CD with truncated binary exponential backoff, and we know what truncated means. Truncated means minimum of k comma 10. That is the truncation. What is binary means? Binary means 2 raised to something. That is binary. Exponential, and because it is power, it is exponential backoff. Then DOCSIS. Okay, so the DOCSIS word is the word used for cable modem standard. Okay, so that is the cable modem standard, and it is used in the cable access network, and it has a frequency division multiplexed channels, and each channel is then time division multiplexed as well. And it is centrally controlled, the allocation is centrally controlled, but you can use random access to make a request. Okay, so when you want to get some data, some channel assigned, you make a random access. Okay, any questions about this? None, then we will move on to the next one. Oh, okay. Switched local area networks. So we will talk about Ethernet frame structure. So Ethernet has a, just like TCP and just like UDP, has a header format that we will discuss, and this header format is shown here. First, there is 64-bit of preamble. Okay. Now that preamble actually is what we would call framing as well, because it consists of 7 bytes of 10101010 followed by 1 byte of 101011. Okay. So that is 8 byte. 8 byte is 64 bit. So before you send anything, you have to send these 64 bit, which are fixed. Okay. Alternating ones and zeros, and then followed by just 2 ones. When you get those 2 ones, then you know that the preamble has ended. Just in case you came in the middle of the preamble, you know that the preamble has ended and the data starts. So the first thing is the destination address, and Ethernet uses 48-bit addresses, and we will talk a lot about that in the next slide. But they use 48-bit addresses as opposed to IP using 32-bit addresses. By the time Ethernet came, we already knew that 32-bit is too small, so we went for 48-bit. 48-bit of destination address, 48-bit of source address, followed by 16-bit of payload type. Okay. So these 16-bit indicates what is inside this Ethernet packet, whether it is IP, whether it is something else. And there are 2 types indicated in this slide. And IP has 0x0800. When you write something like 0x, what does that mean? Anybody? Have you seen 0x before in programming? Yeah, it's hexadecimal. So this is a hex number. So 0800 would be 4 zeros followed by 100 and then 000, whatever, right? ARP is similarly hexadecimal. This is not a decimal number. This is a hex number. And so this is 0806, and there are many other. Basically, that's why they have given 16-bit, so that you can have up to 2 raised to 16 different layer 3 protocols that can ride on Ethernet. So that is the type. And then you have the data, which could be whatever it is, IP packet, IP datagram or whatever, followed by a trailer, and the trailer consists of only 32-bit of CRC. Cyclic redundancy check. Remember, I told you that Ethernet uses a 33-bit divider to get 32-bit CRC. One CRC is put at the end, and so at the receiver, if you get the packet and then the CRC doesn't pass, then you silently discard the packet. Means you do not have any way to tell the source that I didn't get the packet. Okay, and so it's silently discard. The higher layers will figure it out, because the higher layer TCP in particular will say I didn't get the packet, I have a sequence number missing, this and that. UDP will happily continue along without saying anything. So depending upon the higher layer, if they need to tell the source, they can tell it, but this Ethernet doesn't. Second thing, it is connectionless. So you can send the packet anytime you want. You don't have to wait. See, for example, in TCP is connection oriented. So before you can send first data packet, you have to make a 3-way handshake. You have to tell the receiver that I want to send you something, please, and sequence number, etc., etc. That is, we don't do on Ethernet. It is connectionless. Unreliable, and basically no ACK, no NAC, no retransmissions. Alright, totally unreliable. So these were all red flags when we were designing it, but these are all the strengths of Ethernet now, because of all this, it's very cheap. Nowadays it costs only few cents for the Ethernet chip. They don't even ask you, they just put it into the computer. And in every device, actually, almost everything has Ethernet. And then Wi-Fi came along. When Wi-Fi came along, they had to make some of these decisions different. So Wi-Fi doesn't follow much of this. They do follow the CRC. They do use the source and destination addresses like this. but they do have retransmission, because in Wi-Fi, in the wireless, there is a lot more noise and loss. On the wire, there is very little noise and loss. All right. So, are there any issues on this slide that anybody has a question? Preamble, addresses we know, type, and CRC. Any questions? Nobody is raising the hand. So, moving on to the next one. Now, so we first started with something which is called 10 base 5. Now, this may not be in the book, all right, but I think this is a general knowledge that everybody should have. And so basically 10 base 5 meant that this is a 10 megabit Ethernet and baseband. So at the time when we were designing Ethernet, there were two groups designing the Ethernet. One group said that we should have baseband, which means just a clear wire with only one frequency, and one said broadband, which means that they said we want to have many frequencies on the same wire, just like the coaxial cable. So there were both versions, baseband and broadband. The baseband people said that the Ethernet will consist of 500 meter segments. So even though you have 2.5 kilometer, each segment is 500 meter, and then you will put a repeater. Repeater is actually just an amplifier, analog amplifier, so that if the signal voltage went down, it will make it up again. So that is called 10 base 5. That is the original Ethernet. It's also called thick wire because the wire was thick at that time. Then when AT&T walked in, they came up with a thin wire, and that was called 10 base 2, which is actually on the fourth line here. I will come back to third line. 10 base 2, so that was a standard which ran at 10 megabit, but each segment was limited to 200 meters or 185 meters. So 185 meter was rounded up to 2, okay, 200. So that was using RG58 coaxial cable, and that is thinner, okay. And in between there was another standard called 1 base 5, which is 1 megabit over 2 pairs of UTP. Now what is UTP? Unshielded twisted pair, just the phone wire. And the phone wires at that time had, I mean right now also phone wires have 4 wires total, which is 2 pairs. So we said we can do 2 pairs, we can do 1 megabit over it. Then came 10 base T. 10 base T, at that time we gave up on the length business, which was the how long it should be, and we said okay, we will just indicate what is the medium. So 10 base T means we will do 10 megabits on a twisted pair, okay, unshielded twisted pair. And now only with 2 pairs, right? 100 base T4, and then basically after about 10 years we said that instead of 10 megabit we should design 100 megabit. But we needed more pairs now. So we came up with 100 base T4. This is about 1994, maybe, I don't know, maybe not 94 even. I wrote a book actually on 100 megabit at that time, around 1980s, 80. I think it was after 91, so 94 maybe. So 100 base T4 runs on 4 pairs. Now that is why nowadays all the Ethernet wires have 8 wires in it. If you have ever opened the Ethernet cable, if you ever put a connector on it, which sometimes you have to do if your Ethernet cable breaks or something, so then you will notice that there are 4 pairs inside the wire, okay. And so that is 8 T4, and then TX came in because there was another competing standard. There were other competing 100 megabit standard, and from FDDI, which was a competing 100 megabit standard, they took the technology. FDDI ran on optical fiber, and they transmitted it back to twisted pair, so they call it TX. X is for transfer. copy over a crossover or whatever from optical to twisted pair. And then came 1 gigabit. 1 gigabit is called 1000 base T. Then came 10 gigabit, which is 10G base T. And then came 40 gigabit, which is 40G base T. Okay. Now, interesting thing is that now since everything runs on twisted pair, therefore we drop the whole T business and base business. So whenever we talk about now in general public, we say, okay, we have a 100 megabit Ethernet, I have a 10G Ethernet, I have a 1G Ethernet, I have a 40G Ethernet. Everybody assumes that all that is running on unshielded twisted pair. Okay. Although that is not necessary, because a lot of people also use optical fiber for Ethernet. But what they do is they put a kind of what we call transceiver, which takes exactly as it is in the twisted pair and converts into optical, gets into the fiber. At the other end, we just do the opposite. So the fiber standard is not very different from the twisted pair standard. So anyway, so basically, any question about this notation as to how we notate various standards? If you read any IEEE standards, you will find these terms. I don't think the book uses these terms. If you have any question, if you didn't understand some part, this is the time to ask. None? Then I will move on. Now, here is another complication. And again, I don't know whether the book does this or not. Okay, I mean, I was involved in the Ethernet right from the beginning, and so I think there are certain important parts which we have to know. So anyway, when we started designing this, or the PhD thesis was done at MIT, it was called Ethernet. When it went to IEEE, IEEE changed many things, and that is called IEEE 802.3. But by the time the standard came along, and the standard took quite a few years, by the time the standard came along, Ethernet was already in use in many companies, many places. And therefore, the original Ethernet standard, which we call Blue Book, for whatever reason, basically the standard was in a blue color binder, blue color book. So the Blue Book standard is called Ethernet, and the standards which were done by IEEE are called IEEE 802.3. All right. And so the original Ethernet, nowadays we lost that distinction, but here is what happened. Basically, when IEEE came about, people had to change their chips so that they can do IEEE as well as the original Ethernet. So even today, 30 years, 40 years later, every single chip does both the original Ethernet and IEEE 802.3. And therefore, you do not really know whether somebody has original Ethernet or IEEE 802.3, and therefore we just use synonymously, Ethernet, Ethernet. Every time you say Ethernet, most likely you are not really using original Ethernet, you are using IEEE 802.3, which is different. Okay, so what is the difference? In 802.3, they divided the data link into two sublayers. They said media access control and LLC, logical link control, in two layers. Media access control basically was what was done in 802.3 and was different in token rings, which was 802.5, was different in token bus, which was 802.4. So there were a lot of media access control methods. So they said this is the layer which is different in all these different standards, but there is a common layer which is called logical link control, which is basically how do you combine many such tiny networks into a bigger network. So the protocol multiplexing was put into LLC. Protocol multiplexing means that how do you know what is the payload, right? And so interestingly enough, in this frame we have type. Now this is the original Ethernet. Okay, this is not 802.3. So in 802.3, they took this field of 16-bit and put it into LLC. Okay, and here they put the length. Original Ethernet did not have the length field, so you did not know how long is the packet. Basically, when the signal dropped off, then you knew that the packet has ended, and then you did the CRC check. So the IEEE felt that that was not sufficient, and it was not sufficient at least for the token ring guys as well. So they said, why don't we put the type over there and we put the length over here. So anyway, so length. So now, so this field actually, this field which says type has become now T/L, type or length. How do you distinguish between type or length? Well, when you get the packet, you see whether it is less than 1518. If it is less than 1518, then it is a length field. If it is more than 1518, then it is a type field. Okay, so none of the Ethernet types can be less than 1518, and none of the packets can be more than 1518. So 1518 was the boundary. All right, so back to the distinction. So LLC provides the multiplexing. MAC does not need a protocol type field, and it has a length field. So now Ethernet and IEEE 802.3. The Ethernet is shown on the top, where you have the type field of 2 bytes, and that type field indicates whether it is IP, IPX, or AppleTalk. In IEEE 802.3, those 2 bytes are length field. After the length field, there is a LLC header. LLC header. In the LLC header, there is a protocol type field, and that tells you whether it is IP, IPX, or TALK, and so on and so forth. So LLC is like layer 2.5 between the MAC and before the IP. So the length cannot be more than 1518. So last line in this slide says that length greater than 1518 means it is a protocol type field, means it is Ethernet. All right. Now there is so much complication. If everybody understood everything, then please don't ask, but otherwise please ask what is not clear. Does it make sense? What is okay, so the question is, I'll tell you, I will repeat the question. The question is, if you are going to put the type field over there, why do you need this whole LLC thing? I don't know if that is the question. I will tell you, Ethernet didn't really need LLC, but token ring did, because token ring wanted to do retransmissions and connections and whatnot. So they said we will have this layer which will have reverse traffic and acknowledgement and windows and flow control and everything else. So that LLC does a lot more than just give you the type field. So what they did was they defined many different kinds of LLC, actually 4 different types of LLC. LLC that Ethernet uses does not do anything else whatsoever. Token ring users actually did a lot more. Okay, so we are not going to go into LLC too much right now because Ethernet doesn't use any and we don't use any. But basically in the LLC there are again fields, and one of the field is type field, and it is exactly the same 2-byte type field. The same number is used whether it is in the Ethernet or whether it is in 802.3. But the LLC is more for some other protocols than for Ethernet. Does that answer the question? I mean, basically, now with using LLC, you could use any of the IEEE protocols which were done at that time, and still run the same IP, IPX, and IP, IPX don't have to know what is going on underneath. They just give it to 802, and 802 handles this and then gives it back to the IP, as it came from. So this was just to allow multiple MACs, multiple media access control. All right. So the next important thing to know is 802 point addresses, how they are written. So 802 point addresses are 48-bit long. They are always written in binary and hex. So binary is written on the top here in this slide, and hex is written in the next line. Okay. So 1000 is 8 and the next zeros, so 80 colon. So this is called hex colon notation. Hex colon notation because all the numbers are in hex and therefore we don't use the dot, we use colon. Okay, if there is a dot, that means decimal. So this is hex colon notation, and of course the numbers could be from 0 through F. F is all basically 15. And when you go to IEEE and you say, I am a manufacturer, I want to make some Ethernet things, and we did this actually when I was in Nana Networks. We went to IEEE and we wrote a letter saying that we are going to develop some equipment which is going to use Ethernet. So they give you 22 bits. They give you first 22 bits. Actually they give you first 24 bits, but the first 2 bits are fixed. So first bit says whether it is individual or group. If it is 1, that means a group. Sorry, so let me see. Individual or group. If it is 0, then it is individual. If it is 1, then it is group. Group means multicast. The second bit is universal or local. If it is 0, that means universal, and if it is 1, it means local. Now what is universal and local? Basically at the time when we were designing Ethernet, some people said that we should have the addresses which cannot, nobody else can have the address. The universal, so the addresses should be universal. Everybody should have a number like social security number. Nobody else will have the same social security number, right? So that is universal Ethernet address. Other people said, no, we really want to have complete control over my Ethernet, and I want to put in the Ethernet address what floor number, what building number, what closet number, and so on and so forth. So it should really be open up to me. So we said, okay, all right, to satisfy both, we said, okay, we'll give you the local addresses. So if you put that bit to 1, then basically you can put anything in the addresses. If you put that bit to 0, then you have to use the address that was given to your company by IEEE. Okay, so that has to be universal. Now how it becomes universal? The 22 bits are given to each company. You just have to pay $1,000 and you get 22 bits, and those numbers are fixed. So Nana Networks had 22 bits, and then we have to put those 22 bits all the time. The rest of the 24 bit, we just start counting. First Ethernet chip will get 001, and then 2 and 3 and 4 and up to 2 raised to 24. So we can make up to 2 raised to 24 devices or chips before we have to go back to the IEEE and say, oh, we need more. So you get 2 raised to 24 addresses for $1,000, which is very cheap. Now, so the first part, the first 24 bits are called OUI, Organizationally Unique Identifier. By looking at the first 24 bit, I can tell whether it is made by Cisco, whether it is made by Juniper, whether it is made by Nana Networks, or made by who, because IEEE has a list of who was given that number. Okay, so that is Organizationally Unique Identifier. The rest 24 bits are simply assigned by the OUI owner, which means the company assigns number. Okay, so now this is very good. You know why? Because Ethernet address does not change when you go from one room to the next. If your computer and your phone and whatever else you have, they have IEEE 802.3 addresses. I mean basically 802 addresses. These are called 822 addresses. By the way, notice that on the top, the slide, it does not say 802.3 addresses. These are 802 addresses. All 802 protocols follow these addresses, which means 3 Ethernet, 5 token ring, 11 Wi-Fi, and even Bluetooth. Okay, 15. So the idea is that all 802 protocols follow this address format, and so this is basically very good because when you move from place to place, your address doesn't change, and we know that's you. Okay, as opposed to an IP, every time you change the room, your IP address changes, and so the IP is not very mobile. It is not very easy to do mobility with IP. With Ethernet and Wi-Fi, mobility is much easier because we selected this address. We selected globally unique address. Okay. All right. Now there are two addresses which I should indicate: multicast. So there are lots of group addresses, and the group addresses means multicast. and for example, an example of multicast is to all bridges on this LAN. So I am sending this packet to all bridges. Okay. I am getting an echo. Please turn off the microphone. Broadcast. And the broadcast is another important address, which is all ones. If it is all one, which means F, that means to all the stations. Please listen. Okay. So now here is the interesting thing. The broadcast address, is it, now if you look at the first bit, is it a individual address or group address? Yeah, so remember this, 0, the thing written on the top is 0 and the thing on the bottom is 1, is group. So 0 is individual, 1 is group. So this is a group address. Now second question, is the second bit indicate universal or local? Local, right? And so that was basically something that we lived with. It is not a local, this is a universal broadcast address. Anywhere in the world, everywhere in the world, when you send the packet to this address, it goes to everybody. Okay? And there is no building number, nothing like this on the broadcast. Okay, turn off the microphone. So basically, the idea is that this address, even though it is local, this is actually universal. This is the only exception. Okay? Any questions about the addresses? None? Then we will move on to bridges. Now, what is a bridge? Basically, when you have two Ethernets, and let's say you are done with your 2.5 kilometers and you want to go to the another Ethernet, then you connect with a bridge. Okay? And so what I have shown here is two local area networks, LAN A and LAN B. Now, with a bridge, they will look like just one Ethernet, one local area network. And so that's all it shows here is that you can, so station 1 can talk to station 20 or 11 or 10 as well as it can talk to station 2, 3 and 10. The only thing is that the bridge is a layer 2 device. That means it understands the addresses as opposed to the, I said repeater before and I didn't say it, but basically hub is another kind of device. Both of them are physical layer devices. They don't know the addresses, they just do the amplification. Okay. So the repeaters, what they do is they increase the voltage and make the zeros and one look nice, but they don't look at the addresses. Bridges looks at the addresses and decides whether to forward the packet or not. If the address is on the other side, it forwards the packet to the other side. If the address is on this not on the other side, then it doesn't forward the packet. So here is the thing. If station 1 sends a packet to station 10, everybody on the wire will listen. Station 2 will listen, station 10 will listen, and the bridge will listen. They all listen to the same packet. Then the station 2 says it's not for me, it discards it. Station 10 says, oh, it is for me, it gets it. If bridge looks at the address and says it is for station 10, but the station 10 is already on this side, so it doesn't do anything with it, it throws it away. On the other hand, when station 1 talks to station 20, on the top except the bridge. Say, oh, station 20 side, it transmits it on the second LAN, on the LAN B. Okay? The bridges know who is there and they pick up the packets and transmit it to wherever they think they are, the destination is. Now the next question is, how does the bridge know where the destination is? Well, that's another interesting protocol, interesting patent, and this all belongs to digital, by the way, is that the way they are self-learning. They learn because they listen, and so whenever a packet comes from station 1 on the left side or on the top side, there is no version on the top side. So it looks at the source addresses, and then it just makes a note of it. Oh, I have that the station 1 frame, when the station 1 frame came from the top side, so therefore they are on the top side. Station 20, whenever it speaks, the bridge will make a note, and then it will know that station 20 is on the bottom LAN, and so on and so forth. So they are self-learning. They learn it from the source addresses. If station 20 never spoke, then the bridge will not know where station 20 is. And if the packet comes from station 20, then the bridge has no choice but to broadcast the packet, which means that it will send to all the ports. And the bridges don't have to have 2 ports, they could have 5 ports. They could be connecting 5 LANs. So they would send it to every interface except the source interface. If the packet is coming from station 1, it will come from the top. The bridge will look at the destination address, it will see it is 20, then it will send it down because it doesn't know where 20 is, but maybe it is down. Okay, so that is called unknown and multicast. So if the packet is actually, it is called bum traffic. Let's see if the bum word is on the next one. Bum is not here. Alright, I'm going to define bum, B-U-M, broadcast, unknown and multicast. 3 types of packets are sent in every direction, the source direction. Okay, so if whatever wire they're coming on, we don't send it backwards, but on every other interface, if it is a broadcast, it goes to every interface. If it is unknown, it goes to every interface. If it is multicast, it goes to every interface. Is that clear? All right, and it is clear as to how the bridges learn the addresses. All right, so bridges, they monitor all frames on LAN A. Actually, they monitor all frames on LAN B as well. They pick up the frames that are for the stations on the other side. They retransmit the frames on the other side if it is for the other station on the other side. Knows or learns about the stations on various sides by looking at the source address. They are self-learning. Makes no modification to the content of the frame, may change headers. So let's understand that one. When a bridge forwards a packet, it does not change the source address, it does not change the destination address, it does not change anything. Okay, it just sends it as it is. So makes no modifications to content but may change the headers. Now that will come up later on when we talk about some other things, but right now, for the time being, as much as we have discussed, there is no change to the header required, but there are other situations which will come up later on where we have to change the header. Provides storage for frames to be forwarded. So that's another thing, is that when the frame comes in, the other side may be busy, the media may be busy, so it cannot be sent right away. So the packet will be stored and forwarded later on. Improves reliability. Now because you have very small number of nodes per LAN, the collisions go down. So if you have 2000 nodes, you don't put them on one wire, you put them on 10 per wire, and then you put bridges in between them. So that makes better reliability. Improves performance, and again the same thing, it can be called performance because only 10 nodes are competing for that bandwidth. Security. Now that's another thing, is that it keeps different traffic from entering a LAN. So you could say that the bottom LAN in this case is very secure. Nobody can talk to them because they are, accounting department, finance department, whatever. Then the bridge can enforce that policy. So only certain people can get to the bottom LAN, other people cannot get to bottom LAN. So it improves security and may provide flow and congestion control. All right. So flow and congestion control, as I said, is provided by some protocols such as token ring and Wi-Fi, and their bridges can probably provide flow control and congestion control. In Ethernet, we didn't do that and we didn't need it. Okay. That I think would be a good point to stop.